So Kadir Durak is a very active scientist, and he received his PhD from National University of Singapore, and is a young and very active scientist in the quantum technology fields. And he worked on some interesting projects there in cube satellite projects after his graduation, and he worked on some quantum cryptography on the satellites. But today we are going to also see some entanglement as a resource for communication and sensing. So let's welcome him.
Thanks for the nice introduction, and thanks for this organization. I'll talk about entanglement in general as a resource for communication and sensing. Most of my talk is going to be about experiment. Okay, I'll just make some brief introductions to concepts before I proceed, which has been already repeated a couple of times, but I will just proceed with the presentation. So there are two magic of quantum mechanics that cannot be, there is no counterpart in classical physics, which is superposition and entanglement. I will talk about them in a while, but there's this question I keep getting from Richard Feynman. If you understand quantum mechanics, then you know nothing. So if we don't understand anything, we are in the right path. So that's not true. So what he meant was like, we don't find the correspondence of the quantum mechanics laws in our daily experiences. So that's what he meant. Not that we don't understand. Of course we understand. We do something with them. So, but they do not fit into our daily experiences. So this is from the Solvay conference. Zafer just showed about it. So what is Schrodinger's equation? It's just a mathematical equation. What is the interpretation of it? Max Born interpreted it as the following way. So there's a wave function. It's the modulus square of the wave function. Let's say this is the position. It can be any other parameter, but I'm just going to give you the example of position. So this modulus square of this function, or multiplication with the conjugate, gives you the probability of this particle to be at certain point. So if you want to find the probability of the particle to be found between A and B, you just integrate this, and then that gives you the probability. Of course, this is statistical. So quantum mechanics is just combining the linear algebra and the statistical mechanics. So statistically, it tells you where the particle is. Everything is fine so far. The big question of quantum mechanics, well, by the way, these answers are from, I got some rejection, some complaint about this slide previously. So this is from Griffith, the most famous quantum physics book. You can find the introduction chapter. So the biggest problem of quantum mechanics is, okay, well, there's the probability wave function. You make the measurement, you do the measurement, then the particle exists in one point, determined by the Heisenberg uncertainty principle. Everything is fine. So the question that was discussed in Solvay conference was, where was the particle just before the measurement? The first answer, which is the most understandable one, is it was somewhere, you just didn't know it because the wave function didn't tell you. Maybe the theory is not complete. The second answer is it was not anywhere. It did not possess some well-defined position. So it was just spreading along this axis with some probability. So this one is very important. I mean, it's not that it was somewhere, we didn't know it, that's why we had the probability. Classically, that's what we understand. No, actually the particle was not possessing or occupying a specific position. It was everywhere, or defined by this wave function. The third one is agnostic stance. So you're just asking, where would you see the particle? If you measure the particle before you measure the particle, where would it be? So that doesn't make sense. So it's not a scientific question. So Pauli was supporting this idea, Paul Dirac was supporting this idea, and Einstein was supporting this idea. Interestingly, the most craziest one became the right answer. So of course, Einstein didn't want to accept the idea, and then he made this ERP paradox. He talked about this ERP paradox with his colleagues. So basically, he was just trying to show that it doesn't make sense if the particle was not, prior to the measurement, the particle did not possess this parameter that the wave function carries. That doesn't make sense. It occupied, or it had this parameter, we just didn't know it. So for this one, he just got this spin zero particle. It's some radius 2 particles, spin half particles. Then since the angular momentum has to be conserved, one of the conservation laws, if one of them is up, the other one has to be down, and vice versa. And then the experiment is like, if you take this particle like really far away, okay, then you do a measurement, you find that it's up. But since both particles did not have this property, the other one the answer is already known, right? Since we know what this particle's spin was, the other one is already known. But how did this particle know what was this one? Because they did not occupy a certain spin, right, prior to the measurement. So because the distance is so far that it would take lots of time, so and the ultimate speed is the speed of light, so it doesn't make sense. Then there is some spooky action happening in between. That's why he said this spooky action at a distance. There's this famous word. So then Schrödinger talked about this entanglement state. This is introduction to entanglement idea. So he just put this cat. I'm not going to talk about this further, but so that was the classical way of picturing the entanglement. So if the atomic particle radiates, the cat is dead, and vice versa. So that's an entangled state. So then later on, John Bell in 1965, he proposed this Bell equation, violation of Bell's inequality, proven that the quantum mechanics is correct. At least there are no local hidden variables. That's what that experiment says. It has been verified since then experimentally. We can also verify this in our laboratory. The violation of Bell's inequality tells us that the particles are entangled. So the correlations are not classical, and the particle did not have the local realism of having this certain spin prior to the measurement. So it was actually in the superposition of this state. So that's the basic theory about why people are spending so much money. How much money? We are talking about big monies. I mean, like over 40 billion across the world. So this was like 2015 from European Commission report. So please look at the numbers. And now these are the after numbers, like 2018 and 2019. These are the updates. So it's exponentially increasing, just like the quantum computation speed. So exponentially increasing how much people spend money. Why? It's because is useful for some defense stuff. So that's where the money is, I think. The Shor's algorithm in 1995, it talks about finding the prime factors of large numbers, which was used for cryptographic schemes. So, and NSA is one of the biggest providers of these cryptographic suites. And usually they say few decades here, but actually 30 years. They provide the guarantee that no one can break the code within 30 years. But here in this question-answer announcement, which was published in 2015, they said, well, we cannot promise that anymore, sorry. So you have to be careful about the quantum computers. If somebody confidentially get this quantum computer, we don't know about it, so that's why there's no more guarantee that 30 years, for the next 30 years, our cryptographic suites are safe. So that was the first warning. Some more warnings came afterwards. So IBM, half advertisement, half some actual warning. They said move your data today, so do something, otherwise the quantum computers are coming. And here we are. So into this is very recent, 23rd October. This is the Google's quantum supremacy paper. So what is the answer for quantum computer assisted attacks? Is quantum cryptography. I will talk about it in a while, why that's the answer. There are two types of cryptographic protocols, like symmetric and asymmetric ones. Asymmetric ones are usually called public key cryptography. They rely on this prime factorization problem or discrete logarithm. So symmetric keys are relatively secure against the quantum computer assisted attacks. But the key cannot be used forever. Once we get the key, we cannot use for encryption forever. We have to renew the key. Otherwise, there will be some dictionary attack, which means they try to get some patterns out of encrypted messages. So it's not. Then basically, if you use this symmetrical protocols, which are secure against the quantum computer, then you need to keep providing keys to two parties for secure communication, which is a problem. So this is an example of if you want to deliver the keys by people, usually either agents or spies, or banks are using couriers for giving the hard drive to the client. So if you use such a thing, then first, there is still some security problem. Second, well, banks are using right now like that, but if the public keys are not used anymore, then certain percentage of the population, the world's population, has to be either agents or couriers, which doesn't make sense. So that's not realistic. So some solution is needed here. Symmetric cryptography works like this. This is let's say these two parties wants to communicate securely. They want to share a secret message, and then the encryption and decryption protocols, algorithms are well known. So AES, DES, and all the other algorithms are very well known. You can find online and then you can use your own computer. So the security is relying on the key. The key is how you jumble these characters to make it encrypted. And the security of the key relies on secrecy and the randomness of the two-party keys. Here the key used by the part A and part B are the same. One of them is using for encryption, the other one is using for decryption. So secrecy is very important here. We just seen one example here, can be captured. So how do we deliver the key for symmetric cryptographic suites? So quantum key distribution is the solution for this one. Asymmetric ones are using something like this. There's a repository, okay? So you just apply for keys. They provide you some prime numbers. Then once they announce certain numbers, the two parties, part A and part B, they know which key they need to use, okay? So, and by a third party here, let's say we heard what is the large number they announced. Since it's very difficult to find the two prime factors of, let's say, 500-digit number, then it takes like longer time than compared to the human lifespan. So that's why like this cryptographic suite is called protocol is called secure. But then you have to trust the repository, and the computing difficulty is the key here. If this prime factorization can be found, then it's not secure anymore. So there, if we choose to continue with the symmetrical protocols, then entanglement works really good. I will not talk about the other protocols, the BB84 protocol, prepare and measurement protocols. Entanglement-based protocol can be used like this. There's an entangled source, photon source, let's say. Well, I like sources. I know some theoreticians call it fake entanglement, but they are really useful for communication and some other purposes. Because you can make them travel in space without losing their information. So you send one photon here, the other photon here, and then the polarization basis here somehow determines the outcome of here. Okay, so there's a correlation. You can use this for sharing a secret key. Okay, and it is secure because eventually you check what was the polarization information by checking the violation of Bell's inequality. If you violate the Bell's inequality, then you know that they are the legitimate photons used for the other party. You know that they are the actual twin photons. Okay, but how do we create these entangled photons? Let me talk about the spontaneous parametric down conversion process. So there's a nonlinear crystal, it's a Chi2 crystal. You just send some pump beam, some high frequency beam, and then 1 out of 10 to 11, well, I'm telling this number, but I think that theory has to be rearranged. I will talk about it later on. So 1 out of 10 to power of 11 number of photons split into two lower frequency photons. That's why it's called down conversion. The energy is reduced for the down converted photons. They are called signal and idler photons, and their energy and momentum has to be conserved. And that's a typical setup how you can achieve entangled photons. Here there's a laser source here, fluorescence filter, halfway plate for setting the polarization, the cross configured beta-barium boron crystals, which is what we use in the laboratory, and then we put them with a dichroic mirror, we filter the blue light. So after this point, only entangled photons exist. Okay, there are some phase compensation and spatial compensation crystals to make them actually entangled and increase the fidelity. We use this kind of crystals. Then we send them for whatever you want to do, communication or any other purposes. So these are the parameters that we use in our laboratory. So these are the wavelengths. We use 4 or 5 nanometer blue light. We send it to the beta-barium boron crystal. And then we filter the blue light and the signal and idler photons having 780 nanometer and 842 nanometer. How do we choose this? The angle of the crystal. So the crystal is grooved in one axis. When you cut the crystal, you choose certain axis so that it gives you these wavelengths. That's called the phase matching condition. But there are two types of phase matching for achieving entangled photons, critical versus non-critical. Non-critical is you lock the temperature of this device, this crystal, so that the wavelengths of the photons are well defined. But this is usually like less than 0.1 degree stabilization of the temperature is required. And for the other one, the laser beam that you send to the crystal should be like really nicely aligned. Even small angle deviations change the entanglement fidelity, or let's say the quality of the entanglement. How do we understand this? This is a curve that I got like, I don't know, 5 years ago or something. So if you look at this red one here, at this point, or let's say the black points, the visibility, the quality of the entanglement is peak. at 0 angle position. From there, we just detune the angle of the either laser beam or the crystal and see how the entanglement fidelity goes down. As you see here, like around like 100 microradians, plus minus 100 microradians, you're losing a couple of % fidelity. So the entanglement quality is going down. So you have to lock the laser beam that you send to the crystal has to be really nicely adjusted. If you just change even 100 microradians, then you lose your entanglement, which is very critical, especially if you want to do some space-based quantum key distribution stuff. That's why we wanted to use beta-barium boron crystal instead of this periodically poled crystals, like PPKTP or like some other ones. So these periodically poled crystals, they are richer, they are brighter, in terms of their creation of entangled number of entangled photon numbers, but since it requires some temperature locking, it's not suitable for space. How are we going to temperature stabilize certain components? Because what we do here is usually use some Peltier element or thermoelectric coolers. So there are two parallel plates. You just apply some voltage. One plate is getting cold, the other one is getting hot, and then the hot one, you just dissipate the energy to the atmosphere. The gas molecule is getting the energy. You design a nice heat sink, then effectively you're cooling it down. But there's no atmosphere in space. Well, at least not enough. Like 10 to the minus 6 to 10 to the minus 8 millibar pressure is not enough for having a thermoelectric cooler. Then what you can do is like make some large radioactive dishes. Recently I've seen some experiment from Russia. So they just made this large dish. So they radiatively, by sending some blackbody radiation photons, you're dissipating the energy, which is not that efficient. So that's why like beta-barium borate, this critical phase matching is useful for us. And this is a setup where we want to make a compact entangled photon source and send to space and then perform some quantum experiments on them. So these are the first part that I just shown here, like beta-barium borate crystals, phase compensation crystals. Here we split the wavelengths, signal and idler goes different ways, and there are polarizers here. And these polarizers, the angle that between these two polarizers are the interferometer, quantum interference. We are talking about quantum interference. Basically, this entanglement test is a quantum interference test. So by changing the polarization angle between these two, relative angle difference between these two polarizers sets from minus to, in the Bell state, minus to plus state. So but basically you can determine if it's a constructive or destructive quantum interference by doing this. So we wanted to do this test in space, so that was the experimental layout. And then the idea is miniaturizing it to the like something like credit card dimensions, and put in a satellite and send to space, and then send the photons to Earth and see if the correlations are kept in space. Like around 3 years of work, we miniaturized the quantum entangled photon source, which is inside this black part, and the driving circuitry is behind this. Well, this is just upside down. So these are the driving circuitry for that, and these are the dimensions and everything. Like it's pretty small, and we were able to operate the source, including the detectors, with a 9-volt remote control battery. So, and like lots of testing, so if it can survive during the launch to the space. So we successfully miniaturized it, make a compact source, and then like we want to have some launch trials. First a balloon test, some weather balloons goes up to like 35 to 40 kilometers. It exploded in 35 kilometers, that was published, it was successful. The second one, NASA's rocket exploded in 2015, that's the picture of it, and that was the satellite. And the third one is successful, but this one somehow is a more famous paper than the successful one, because usually like if you talk about entangled photons, like don't breathe, don't get too close, you're too hot, so you will change the temperature, and then like the alignments will be gone, something like that. So usually like extra measures are taken so that, you know, the entanglement properties are kept. But here like it goes up to like 200 degrees and like g, like an acceleration of around 54 g, which was a huge explosion, and it survived through this explosion. Well, when we first seen this, we got the news from NASA that, you know, it survived. The first reaction of the professor was accident in an accident. But later on we realized that actually it was over-engineered. We over-engineered the source. And that's the layout of the source. I'll not talk about this in detail. So then we want to improve the source. How do we improve the source? We can increase the entanglement quality, which is the entanglement fidelity. We can have improve the collection optics. We can have more entangled photons per second. And the collection efficiency and the brightness will improve the rate for the quantum key distribution if you have your source in satellite. So there was a paper here, as you see here. We had this model where this Volkov of the pump beam for a 5 nanometer, and this is the collection optics. The overlap region determines the entangled photon shape. As you see here, we were expecting, for signal and idler, we were expecting some peaks like this, the spectrum like this, because the crystal was long here. This was a 15 millimeter crystal, but experimentally we got this yellow curve. The reason for that is we said that, okay, maybe the length is long, but we are collecting from a very limited part of it. But apparently this was a wrong picture. So unfortunately, I wrote the paper, but so. Because, well, 2 years ago I came Turkey, I came Istanbul, so we wanted to see the entangled photons. Maybe if we can see the entangled photons with a camera, a regular camera, we can actually tailor how the mode shape looks like, and then we can have more entangled photons. That was the idea. So then we first calibrated the camera. Well, it's just a regular camera. I mean, I got it from Sarkan Hoca. I don't know where he is, but yeah. Calibration means just subtract the dark current of the camera and remove the background, either switching of the light or putting extra strong filters. So basically it works linear as long as it was an 8-bit camera. As long as you don't go to exceed this number, 255, it's perfectly linear. So then you can use it like a power meter to see the entangled photons. And here how it looks like. So basically, if you look at this picture, if you remember the, okay, so the pump beam goes like this, and if you change the crystal angle, we designed everything for collinear regime. So signal and idler photons go in the same way. If you rotate the crystal angle, they will change their direction. Then you will see, because of the circular symmetry, you will see this donut shape. And then if you rotate the crystal angle, the circle is going to be having larger and smaller diameter. So here we have two crystals, cross correlation. When they perfectly overlap, we have the entangled state, because they have to be indistinguishable. So that's how it looks like on the camera. What we are doing is just changing the angle of these two crystals. The coloring is added later on. It's not the actual color. It's just like some black and white image. But we had to take out the infrared filter from the camera. So when these two circles perfectly overlap, they have this entangled state. Normally there's Volkov, but because of these compensation crystals, they can perfectly overlap. Okay, how do we stop this? Okay, so we now can see the mode shape with the camera. How do we continue? First of all, in the literature there are papers saying that you cannot collect the photons, all the entangled photons to single mode fiber, and that follows this. If the crystal length is L to the power of square root L. It just goes with square root L, something like this. We also seen like this. I mean, if you couple the entangled photons into single mode fiber, we realize that it goes like this. But with the camera, it goes linear. It's supposed to be linear because we know that it's the chi2 effect, which means the power of the number of the entangled photons goes with the linearly with the intensity of the light, which is the square of the electric field. But we cannot collect them to a single mode fiber. Then we want to understand if what we see that makes sense or not. So the crystal that we cut was like 28.8 degree crystal cut. That's actually 0 degree when we go to normal to the crystal. And then we just change the angle of the crystal. And that's the angle of the crystal. And this is the signal and idler wavelengths conserving the momentum of the down conversion process. But here we realize something. I mean, there's no elliptical mode shape, which exists in almost everywhere in the literature. We didn't see that. So what we see on the camera, our analysis doesn't fit to the literature. Let me talk about this. I mean, these are some of the papers that you can see the mode shape. Like this is the Volkov of the pump because extraordinary beam. Birefringent crystals work like this. If you send an extraordinary beam, even if you go normal, it gets deflected. That's called Volkov. But the ordinary polarized beam, it just goes like travel without changing the angle. As you see here, the Volkov is changing the pump beam changing the direction, but entangled photons are still having the ordinary axis here. You can see this picture almost everywhere. There are some other examples, like respected journals here, but the problem here is, well, we don't see that in the camera. 5 minutes. Okay, when we get back to the theory, we realize that there is something wrong. Okay, ordinary axis is well defined, but the entangled photons should follow the momentum of the pump beam, which means even if you give some angle, if you have this non-collinear geometry, it has to be cylindrically symmetrical around the pump beam. That explains this. So I think this, there's one correction in this part, but I will rush a little bit because I'm running out of time. So when we change the crystal angle, we realize that there's some asymmetry coming out. I mean, you can see it from this picture as well. So there's an asymmetrical shape here. The reason for that is because we focus the pump, and because of the Snell's law at the very simple explanation. We were really looking deep, but we realized it's just Snell's law. That prevents us coupling the entangled photons into single mode fiber. So now we have a really bright source. How bright? Something like this. We have 10.4 million pairs per second and per milliwatt input power, and we can collect like around 500,000 entangled photons into single mode fiber per milliwatt. Again, if you send like 100 milliwatt of pump power, then it's going to be 100 times. It's extremely bright. The best value that I know of so far is 96,000 entangled photon pairs per second with beta-barium boron crystals. I'm talking about single pass, not a cavity case. So we have a really bright source. What do we do with them? We talked about, and then there's this famous thing that people were asking me, like, is that actually real or not? The quantum radar news about China. So they just have, this is their explanation, by the way. They have the entangled photons, and they just keep one of them with an optical delay, and then measure it, and then keep the information, and then send the other one with a search telescope to see what is coming backwards, and then they check the entanglement correlations. If it's the legit photon, they can understand how much is the delay of this photon. From there, they can understand the distance. That was the basic idea. They said like they had this from 100 kilometers, but there are some different ideas about this news. Some people says it's really important. I mean, like they get this, and then some people say don't buy that. I mean, it's not possible. So I wanted to test if it's possible or not, because we have really bright source. So we wanted to see if we send entangled photons, are they actually coming back or not? So that was the experimental setup. Here in this experimental setup, in this result, we just looked at the time correlations and not the entanglement properties, but we can also check the Bell's inequality, violation of Bell's inequality. That tells us if the photons are coming to our detector, are the legit photons or somebody's trying to fool us or not. That's one of the advantages of quantum radar, let's say. By the way, when I say radar, there's the radio term here that pisses off the radar people, but well, I don't know what to say, that's why I'm using this term. But this is not in microwave frequencies. This is in optical and near infrared band. So, but that tells us actually the photons can be used for this business or not. So what we do is pretty much the same as what you see in the Chinese paper. So we just split the entangled photons, signal goes this way, we just record the timing information of these photons, and then send the other one with a telescope. And then if any photons are bouncing backwards, we collect with the same telescope, and then they go upwards now because there's a quarter wave plate here. And then we look at the time correlations here. And then when we have the cross correlation function, with a certain delay, we see a peak at the coincidences. So that tells us what is the extra path that these idler photons traveled with respect to the signal ones. And they're moving with the speed of light. That tells us what is the distance of this object. So that is, here's the preprint for that. So this is, like basically I went up to like 1.25 meters here, but now we can go up to 4 meters. That's pretty much the limit we can have in our laboratory. So this is the experimental setup. It goes down with the 1 over r square. R is the distance with the object and the source. So it goes this way. And the cross correlator looks like this. I mean, like if you have one object far away, you get something backwards, and then we get this one. If you put something like side to it, like with a different distance, you will see something like this. And then here is the time axis. How much is the time? So 3 nanosecond means something like 1 meter. 3.3 nanosecond, yeah. So because it's moving with the speed of light. So this delay tells us where the object is. So if you put two objects, you will see like what their positions are. So basically we can use these entangled photons for seeing them. the entangled photons we used here are like near-infrared photons. So then we made some speculation if actually, what is the ultimate limit that we can achieve with the current technology? Well, the entangled photon creation, we already have really bright source, which is much stronger than what the literature suggests, because we are checking with this camera, not the single mode fibers coupled to the detectors. And we can have this by source multiplexing. We can put lots of sources side to side and have really like bright source. That's no problem. That's not the technological limit. And the photon detector situation, again, we can put beam splitters and have lots of detectors side to side, and then they work in parallel. We can overcome this limitation. Timestamp resolution right now, what we have is like 80 picosecond, which is pretty good. It can even improve, but this is good enough already, because the bottleneck is coming from somewhere else. It's the APD timing jitter. That's around a couple of hundreds of picosecond. Like in our case, like 300 picoseconds. Let me explain what it looks like here. Okay, so the thing is, when a photon comes at time zero, time t is equal to 0 here at the detector's active area, it takes some delay until we detect that pulse, okay? Or the digital pulse is created. But that is not constant. It goes back and forth. It's a distribution. And that distribution means if these two photons are really close to each other, the previous one can go be like in front of the other one. Then if you're looking for entanglement correlations, we will see something wrong. On the other hand, if you're looking for coincidences in the cross-correlation function, you will miss this coincidence, which means even if there's something in front of you, you will not be able to see it. So that's why like this 300 picosecond, how do we get this 300 picosecond, by the way? From this picture. So if you look at this peak, it's not like one point. The coincidence is not having a peak in one point, it's a distribution. It's because photons are like moving back and forth. That's called timing jitter. In Turkish it's zaman titreşimi, zamansal titreşim. So they go back and forth. Because of that, you're losing some photons, or the coincidence might be a little bit back or forth, before or after where it's supposed to be. Because of that, we see some peak like this. If these photons are too many, if they come closer to each other with the Poissonian distribution, then basically you may lose the correlations. Because of that, the limitation is coming from this APD timing jitter. There are some other problems like weather conditions, stealth materials, and tracking moving objects. For these two, for weather conditions and stealth materials, wavelength multiplexing can be used. Basically, we can change the crystal angle and then define what wavelengths we want for the signal and idler beams. We can engineer that. So that's no problem. But tracking moving objects, there are two things that we can do for that. We use pulsed lasers and then see how much are the pulses having this relativistic delays or time dilation or contraction in this case. So both can happen if the source is coming towards us or the other way around. So because of that, the pulses are going to have some delays, or they will contract in time. Or we can use some Doppler shift laser, dedicate some of the entangled photons for checking the spectrum. From there we can see how much the wavelength is shifted from the Doppler shift, which is similar to the classical radars. So basically with these current limitations, 10 gigapairs per second entangled photon rate gives us around like 300 meters. Beyond 300 meters, you will have a coincidence rate of less than 100 coincidence rate. Here, what we use is like a black anodized aluminum, which is something very similar. You can find in the laboratories, because in the optics laboratories, you don't want any reflections. You don't want the photons to scatter around. That will destroy your quantum correlations. That's why these materials are coated with the black anodized. So that's what we used here. And well, what can be done is. So basically, if we can have this wavelength multiplexing techniques, use multiple sources with different wavelengths, we can go up to like 1 kilometer with this technique. And then there's something else called ghost imaging, quantum ghost imaging. Well, entangled photons are created with the spontaneous parametric down conversion process. We talked about the momentum conservations. If they are going collinear, they are collinear. If one of them has angle, the other one has to have some similar angle so that their momentum is conserved. We can use these momentum correlations for getting the two-dimensional image of this object, and the third dimension is coming, so there are some corrugations in the surface, so the photon reflected from this point will travel more path than this point, so that gives some third dimension from the cross correlation functions. We can check all these things to get the 3D image of the object. So that's my friend from Singapore. So yeah.
So I have a question regarding the last part of your talk. I thought the point of the quantum illumination and quantum radar is not that you can just detect the target by means of one photon entangled pair, but rather that you have advantage compared to, say, detection with coherent states.
Okay.
Do you see that?
So here, well, in this experimental setup, the advantage, let's say, with respect to the classical radar is basically you can check if the photons that are coming to your detector is legitimate photons coming from the object or somebody is trying to spoof us. So we can check that with the entanglement, violation of Bell's inequality. If the object doesn't have some certain, well, with certain techniques that can be also changed because the polarization can be shifted. You can put some coat the object with some material that is having some halfway plate, let's say. You can change the polarization. If you don't do that, whatever is coming backwards is like having the same polarization, linear polarization. Then you can check the entanglement correlations, violation of Bell's inequality. That tells us if somebody is trying to spoof us or those are the photons that we have the twins as reference in the laboratory. The other advantage is that we are working in the single photon level. Okay, and which is hard to detect because we are working in the single photon level. The analogy can be done to the LiDAR actually. LiDAR is closer to this technique. So with LiDAR, you're sending actually laser pulses, which can be detected. Here we are working with the single photons, hard to detect. Even if the other party detects, cannot spoof.
Well, I mean, you can reduce coherent states, but
yes, you can still do. But the problem is still you cannot prevent the spoofing attacks. Yeah, if somebody can detect, even if low level, they can send the similar pulses and do the spoofing, so that as if the object is going somewhere else. But here, we know our photons with the laws of quantum mechanics, by the violation of Bell's inequality. So that's the advantage. It's not a quantum radar. I use the term, I try to explain, radar because I don't know what to say. It's not radio frequency. We are working with the near infrared, yeah. So. But there are also experiments parallelly being done in Austria. They are having the photons, entangled photons in the microwave region. So that's a different experiment, but there are some problems with that as well, like conversion efficiency or like the brightness is really low and stuff like that.
From Seth Lloyd, I think there is a paper that he claims that even if we do not observe the reflected entangled photon, we can again enhance our radar. Do you deal with such?
China says that, right? Seth Lloyd. No, okay. That's a really nice question. I keep getting the same question actually. So it's the same thing. I mean, in this proposal, they say that like we measure these photons. If this photon like hits to some object, you can understand it here. No, the entanglement doesn't work that way. Entanglement doesn't work that way. It has to be measured in the same polarization axis. We are talking about polarization entanglement here. And then the timing of the photons should be recorded. If you know nothing about the other photon, it doesn't work that way. Yeah.
But it's just speculation.
Yeah, it doesn't work that way. I don't think.
Ghost imaging isn't relating to that, or is it not? No.
Ghost imaging works like this. I mean, in this picture, I didn't have time, that's why I didn't talk too much. So let's say there's a photon. We measured one photon with a camera and record the position of the pixel where the photon hit. Okay, we record the timing of it and the position of the address of the pixel. Okay, then we send some, like the twin photon goes this way and then it hits and comes back. This one is a bucket detector. Where is it? Okay. Okay, here. So this one is a bucket detector. It comes here. Bucket detector means that either there is photon or no photon. We just know the timings, but from the time correlations, we know where the twin of this photon on this pixel, which pixel is that. Then, by looking at the coincidences, you can have the two-dimensional, let's say, silhouette of the object. Two-dimensional information is coming from this part. And the delay that you have is telling you the depth information, and the timestamp unit's time resolution, which is 80 picosecond, tells you like 2.5 centimeter. Yes, 2.5 centimeter resolution in depth. So basically, you can get the image of this 3D object, 3D image of the object. That's how it works.
Let's close the session by thanking all of our speakers today.